Welcome. This lecture is going to be on Newton's law of universal gravitation, and this was Newton's explanation of what gravity was, why there's an attractive force between all objects that have mass, and specifically why there's an attractive force between us and the Earth, or the Moon and Earth, and things like that. So let's start with, we've got the Earth here and we've got the Moon here. And let's say that these guys are some distance r apart, and this distance r is not from the surface of the Earth to the surface of the Moon, it's from the center of the Earth to the center of the Moon, the two objects' centers of mass. And let's give the Earth a mass big M, and let's give the Moon a mass little m. And Newton's big idea was that the force that causes an apple to accelerate towards the Earth when it falls off of a tree is the same as the force that keeps the Moon in orbit around the Earth. And based on a lot of math, he came up with the following. He said that the force due to gravity between two objects is 1, attractive, and 2, is equal to the magnitude of some constant, g, which is called the universal gravitation constant, times the mass of one object, in this case the Earth, times the mass of the other object divided by the square of the distance between their centers of mass. Alright, so big G, as I said, is the universal gravitation constant. And Newton didn't know what it was. In terms of things on Earth, he knew that big G times the mass of the Earth was going to be a constant, and he could figure out what it was. He could guesstimate the mass of the Earth based on an estimated density of the Earth and the radius of the Earth and come up with an estimated value of big G. But big G would have to be measured. One thing Newton knew was that big G would be small. It took a very smart guy named Henry Cavendish to come up with what the an experiment that would actually measure big G. And it was a genius experiment. I'll show it to you in class, but here's the value that is currently accepted for big G, 6.67 times 10 to the negative 11th. And the unit on here is newtons times kilograms. Oh, hold on, I gotta look it up. Now I can't remember it. Here it is, newtons meters squared over kilograms squared. Such that when you insert big G into the equation, you end up with a unit for Newton, because we've got kilograms squared on top here, meters squared on the bottom here, and so those have to cancel with our unit for big G and end up with a unit for newtons for the force of gravity. So that's the basics. The force of gravity between two objects is directly proportional to their masses, and it's inversely proportional to the square of the distances between them. Now, from this equation and our understanding of uniform circular motion and other equations, we can derive all sorts of useful equations from this. It's important to note that this works for spherical objects, and we're talking about the distance between their centers of mass. Even if we're talking about two hollow spherical objects, we'd still be calculating the force of gravity between them based on this. So now here, in more general terms, big M and little m don't have to be the mass of the Earth and the mass of the Moon. They can be the mass of the Earth and the mass of an orbiting satellite. It can be the mass of the Sun and the mass of an orbiting planet. So let's just be more general here. Big M is going to equal the mass of the planet, or the larger mass, little m, is going to equal the mass of the satellite. All right, so again, Newton's law for universal gravitation. We've got Fg is equal to big G, big M, little m over r squared. But we've dealt with the force of gravity before. The force of gravity is simply the weight of an object. So if we're talking about, let's say, I don't know, the surface of the Earth, the force of gravity acting on you, if you're little m, is just going to be little m times g, where g is the acceleration due to gravity. If we're talking about the surface of the Earth, then g would be 9.8 meters per second squared. So since both of these are equal to fg, we can set them equal to each other, so we end up with big G, big M, little m over r squared is equal to little m times g. Obviously the little m's cancel out here, and we have an equation here for the acceleration due to gravity because of a massive object at some distance away from that massive object. So more specifically, we've got little g is equal to big G times m over r squared. And if we plug in mass of the Earth and the radius of the Earth, we should come up with a number that's really close to 9.8. And here we can see why, since the Earth is not a perfect sphere, we have different accelerations, slightly different little g's, depending on whether you're at the equator or you're at the North Pole or whether you're on top of Mount Everest or down in the bottom of the Grand Canyon, because r is going to be slightly different. Does it matter that much? No. More generally, little g is called the gravitational field. So this equation will give us something called the gravitational field due to a massive object. So if we've got a massive object, let's say it's the Earth right here, then if we plug in the radius of the object, r, and the mass of the object, we can find a value for little g at the surface of the Earth. And that value for little g is going to have a magnitude and a direction. The direction is pointing straight in towards the center of the Earth. And we know that as the acceleration due to gravity. Well, let's say we plugged in values for here, a different r, the same m. Little g is going to be less, so we would have a vector that is pointing still in towards the center of the Earth, but smaller. If we found the value for little g out here, it's going to be smaller still, and smaller still as we get further out. And wherever we do this, if we're the same distance from the center of the object, we're going to get arrows that do the same thing. They get smaller and smaller and smaller as we move away from the object, but they all point in towards the center of the object. So what we have here is a visualization of the gravitational field. If we can envision arrows all around this guy, all of them pointing in towards the center, and all of them decreasing as the distance from the center increases, we've got a visual map of the gravitational field. And what the gravitational field tells us is, generally, if we've got an object right here, then it tells us what the acceleration due to gravity on that object would be, and we can see that that is regardless of the object's mass. So this is a very general equation. The mass of the object doesn't matter. All that matters is the mass of the planet that it's attracted to and the distance that it is away. So the gravitational field equation is very important. So now let's combine Newton's law of universal gravitation with the stuff that we've already learned about uniform circular motion. So we're going to look at orbits. So this would be a circular orbit. We're going to start with that. And with a circular orbit, we know that we've got this satellite, little m, out here. We've got this planet, big M, down here. They're a certain distance r away. And now this satellite is orbiting the planet with an orbital velocity v sub o. And we recognize that as a tangential velocity. So since there is a force of gravitational attraction between these two, we can draw it in here. We've got F sub g, the force of gravity, that's going in towards the center. We also recognize that as the centripetal force that is making the satellite go in a circle. So we then can set our Newton's law of universal gravitation equal to what we know about the centripetal force, mv squared over r. The r's are the same, the little m's are the same, and we get to do some cancellation. And now we've got big G, big M over r is equal to VO squared. This is not V naught, it's the orbital velocity or the tangential velocity of the satellite. So this equation is great. It relates the velocity of something in orbit to the mass of the thing it's orbiting around and the distance it is from the center of mass of the object it's orbiting around. Okay? So this is very handy when we're talking about orbital mechanics. And if this orbit is a circle, we can take it one step further, because the orbital velocity we can relate to the circumference of its orbit, which is going to be 2 pi times r, that's the distance it travels around the circle, divided by the time that it takes. And we're going to say capital T here. And capital T we're going to call the orbital period. And it very simply is the amount of time it takes for the satellite to go once around in its orbit. And so now we can plug this, 2 pi r over the period, into our v0 squared equation. And let's do that here on the next page. And I made the mistake. It's not v0, it's orbital velocity. So we've got big G, big M over r is equal to the quantity of 2 pi r over t, and that whole thing is squared. Now we're going to do a little simplification here. Left side stays the same, and on the right side we have 4 pi squared r squared all over big T squared. And let's get rid of the fractions, because nobody loves fractions except for me. So we'll move this r up to the other side. We'll multiply both sides by big T squared, and we end up with big G m T squared is equal to 4 pi r cubed. And this is extremely important. This was Newton's confirmation of Johannes Kepler's third law of orbital mechanics, which said that the orbital period squared is proportional to the orbital radius cubed. If we rearrange and divide both sides by big G, big M, we get T squared is equal to, I forgot a squared down here on the pi, 4 pi squared over big G M, that whole thing, times the orbital radius cubed. So we do see that the orbital period is indeed proportional to, right there, r cubed. And 4 pi squared over big G M is a constant if we're talking about orbits around the same object. So, for example, we can say that Mercury's orbital period around the Sun is proportional to its orbital radius around the Sun. And the mass of the Sun is going to go in there in that fraction. And Earth's orbital period squared is going to be proportional to Earth's orbital radius cubed. And we can do that for any planet orbiting around the Sun. So as I said, this was one of the most important facets of Newton's orbital mechanics, his law of universal gravitation, because it totally confirmed what Kepler had theorized by direct observation and shown to be the way that the planets orbit the Sun. So this was fantastic. So here we have Kepler's third law. And you're going to be able to use that to look at ratios of periods to radii of planets orbiting the Sun in your work in this class. You may have heard it said that if there was a body of water large enough and you put Jupiter in it, Jupiter would float, because it has a density, an overall density, less than 1. And the question always is, how the heck do we know that? Well, we know it based on Newton's law of universal gravitation. So go back to this equation. Little g is equal to big G times the mass over the radius squared. So let's say that the mass, big M, is the mass of Jupiter, and r is the orbital radius of some of its moons, its satellites. Well, we know that mass is related to density and volume. So let's go ahead and throw in a density equation here. The density of a sphere, and we're going to say that Jupiter is roughly a sphere, is equal to its mass divided by its volume. And the volume of a sphere is equal to 4/3 pi r cubed. So then we can use this. We've got rho times v is equal to m. Plug in the volume of a sphere. rho times 4/3 pi r cubed is equal to m. Now we can throw this into our equations for m. And this would be maybe the mass of Jupiter, and this would be the radius of Jupiter. So we would just need to be very careful with our radii, because this radius right here is the radius, or the orbital radius. So if we're talking about what is the acceleration due to gravity on a moon orbiting Jupiter at some orbital radius, then those two r's would not necessarily be the same. If we're talking about the acceleration due to gravity on a planet, the surface of a planet, then the two r's would be the same. Okay, so we could directly, just by measuring the acceleration due to gravity on the moon, take a hammer up there, time its fall to the ground, measure that acceleration, we could use that to find the density of the moon. Pretty powerful stuff. So anywhere we have a big M, we can plug in this and have an expression that allows us to deal with density of a planet as well, or density of the sun even. So that's it. And we're going to put this to action on a problem set. See you next time.